Here I'm going to demonstrate that we should use nonlinear regression if we want to get the parameters in the Michaelis-Menten kinetics expression rather than something like the Lineweaver-Burke linear regression. And so first let's look at what the equation is for the Michaelis-Menten kinetics. This is what shows up often in bioenzyme kinetics. So V is used for the rate, and V max is one of the parameters. S is the substrate concentration, Km the other parameter, and S shows up again. So remember, this is the rate, and typically we vary the substrate concentration. So this would be the independent variable, and we measure the rate. So this would be the dependent variable. There are other screencasts that describe how this rate expression arises. What we're interested in here is comparing if we carry out nonlinear regression and then we carry out linear regression, how these differ in fitting the data. So both types of regression assume that the data scatter is going to be in a Gaussian distribution around the dependent variable, around the rate in this case. It's a reasonably good assumption for nonlinear regression. We're varying the substrate concentration and then measuring the rate. Now, if instead of using nonlinear regression, we linearize, and let me write down the expression. I won't derive it, but it follows fairly straightforward. So if we're to plot 1 over the rate, 1 over the velocity, versus 1 over the substrate concentration, we expect a straight line, and then this would be the intercept, and this would be the slope, and so this is a way to fit the data. However, what we're doing is compressing points that are at the high substrate concentrations, and we're putting more emphasis on points at the low substrate concentration, and these are ones that are often the least accurate. Remember that in regression, we're assuming the scatter about the measured values is the same, but when we take the inverse of the rate, that's no longer true. So let's look at values that we get. We're going to use some data from a reference. So let me pull up that data. So what I've done, I've taken data, show it in the table from reference 1. This reference is at the end of this screencast. Done nonlinear regression, and notice that the confidence limits are relatively small, which is what we look for to have a good fit. And then I compared it to the Lineweaver-Burke linear regression. A couple things to note. First, the values for Vmax and Km are really quite different. Notice how large the 95% confidence limits are. For the A0, the Vmax, it's almost as large as the actual value. So this is really a red flag saying this is not a very good fit. So here I've plotted the rate versus the substrate concentration. We're just showing in micromoles. Obviously, it's a micromoles per volume. The green squares are the actual data that we're trying to fit. The blue line then is the nonlinear regression. You see it's a pretty good fit. The Lineweaver-Burke fit, the linear regression, the orange line and date endpoints, and notice it's not a very good fit. It's really quite a bit off from the data. So it's clearly an indication this is not a good approach to use. We also can look at some of the other approaches that are used. So linear results using a couple other models. Again, linear regression, but a different arrangement of the equation. You notice I've repeated here the nonlinear regression values so you have a comparison. Notice that the value for Km is quite a bit different. Contrast the fit using the Haynes-Wolff linear regression. It is relatively close. So this, of the ones I show here, this model is clearly much better. Excuse me, this linearization, I should say, is clearly much better. But in general, nonlinear regression is still the best approach to use. And I've listed a couple of references that discuss this in more detail, but the final takeaway is that we should not be using the Lineweaver-Burke linearization to determine Michaelis-Menten kinetic parameters. And we should instead be using nonlinear regression.